A. Because tau is equal to CR, therefore C must be tau over R 0.8 right, where's my set of answers? Bad at this today. Right, because we know that tau is equal to CR, we can rearrange that, divide tau by R, we get 16 microfarads for the capacitor. The capacitor voltage under discharge is the starting voltage times e to the minus t over tau. You need to rearrange that. So I'll put the 20 that we're looking for in there. That's the starting voltage. And the time constant is 0.8 of a second. I've divided by 100. 20 of 100 is a fifth, so I've just simplified that. Okay, now, I think this result come from Mr. Byrne here doing a bit of manipulation that we wouldn't normally do. Because here we do ln of a fifth is equal to minus t over 0.8. Yeah. So minus t is 0.8 ln a fifth. T is minus 0.8 ln a fifth. The answer comes out to 1.29 seconds. I think what he's done here is he's because there's minus negative sign there, that's like he's done 1 over, so he's took the reciprocal of both sides. His work solution can be a bit confusing at times. You should get 1.1 seconds. Instantaneous current after 0.5 of a second. So the initial current flowing is V over R, 2 milliamps, and then we can in that formula calculate 1.07 milliamps. Am I going too quick for anyone? I put solutions up anyway. Instantaneous voltage after 1 second. So we got minus 1 in there for T. 28.7 volts. And after 5 time constants, the resistor and capacitor, which are always equal to each other, has dropped to 0.674 volt, worked out to be about 99.3% charged. If you remember 5 time constants of charging, we were 99.3% charged, and now on discharging we're 99.3% discharged after 5 time constants. Alright? Yeah. So that's what I'm on about this consistent time, and we can use that. We know how long it's going to take, and it's always going to take the same amount. Alright? Right. Moving on from that, we want to look at the inductor. Now, in your notes there's some background about induction. But when we apply, or when a current flows in an inductor at Faraday's law says while the flux is changing, while the magnetic field is changing, and that'll be changing when the current is changing, you'll get an induced EMF, right? So you'll get an EMF produced across the coil while the current is changing. Also, Faraday's second law states that the size of that EMF is proportional to the rate of change of current, and you've got that in your notes. So the faster the current is changing, the faster and more voltage is induced in that thing. You've also got that's relative to the rate of change of flux and the number of turns in the coil. So if you put more turns on the coil, you're going to get more inductance and therefore a higher voltage induced. Okay, what I'm a bit more interested in is doing what the transient response is, like we've done with the capacitor. Then there's another law called Lenz's law. That law says the induced EMF, according to Faraday, will always oppose the change that's causing it. So when the current through the coil that you're applying is changing in that direction, the inductor is inducing a voltage that will try and push a current back in the other direction and oppose it. And that's why we get the effects that we're now going to talk about. Right? So the inductor is a little bit more difficult to get and a bit more difficult to talk about in detail than the capacitor in that respect. Things happen a lot faster. It's more difficult to create a long time constant with an inductor. Alright? So the major difference is if we got an inductor here, okay, and we apply a voltage to it, V, and we've got a resistor in the circuit as well to limit the current, we get a current flow. Initially at switch on, okay, the current is looking to rise very quickly so if we have 10 volts and 10 ohms, it's looking to go from 0 to 1 amp instantly. Yep, all get that. So at switch on, we've got a very high, because the current is trying to go up very quickly, we get a very big, we've got a fast rate of change of current, and therefore our induced voltage across the inductor is high. Yeah, but what that does is that sets up a current in the opposite direction that reduces the current rising. So what happens is the inductor voltage, the induced voltage across the inductor, over time after switch on, tends towards zero in an exponential way. Yeah. So it starts off the applied voltage and it decays away according to that formula. Notice though that tau in an inductor circuit is equal to L, the inductance in henries, divided by the resistance. So tau, the time constant is different. Yeah. So instant we switch on, we get a high induced EMF, but because that opposes the rise in current, it decays away to nothing. Okay. I'll just put a note on there that is the induced voltage inductor. On the next page, we're looking at the current flow. Remember what I said initially in the previous slide? This current is trying to go from there to there instantly. Yeah, V over R. Because remember, what's the resistance of an ideal inductor? no ohms. Yeah. So that's an ideal inductor and a series resistance. Therefore, initially we're doing V over R, 10 volts, 1 amp. It's trying to go from 0 to 1 amp instantly. Yeah. But trying to do that causes this fairly big voltage across here trying to send a current in the opposite direction. There's I, look, going up that way, but that's trying to send a current that way. It's never as big as that current, but what it does is it's opposing it, so it's slowing the rise down. But eventually, over time, about 5 time constants, it reaches steady state, V over R state. So in the case of our example, if we're 10 volts and 10 ohms, it gives an exponential rise to a limit of 1 amp. Yeah? All get that? And I'm sure you know how to use that formula, exponential rise to a limit. No dissenting voices? And then, so this is the circuit current I on switch on. See, these slides were a little bit last minute. I didn't even get the title wrong. Right. And then lastly, the voltage across the resistor, the shaft is always going to follow the current that's flowing. So if the current rises exponentially to a limit, then the resistor voltage is going to rise exponentially to the limit being the applied voltage. So this is the and like I say, if you can remember these principles, remember them laws, and particularly Lenz's law that the induced EMF opposes, you can work out what shape these curves should be, and you should know that they're either going to be a rise to a limit, the bracketed term with 1 minus e to the, or it's going to be an exponential decay to 0. Yeah. Right. And if you think about the time constant, remember, if we have a higher inductance, we get a higher induced EMF. So if you think about increasing L, we're going to increase the time constant. Yeah? Right? We've got an example there on inductor from switch on, but I just want to skip ahead and look at inductor at switch off, and then you can work on the 2 problems between now and the end of the session. So inductor at switch off, okay, in actual fact we've got this field built up in the coil that once it reaches steady state it's going to stay constant like an electromagnet. When we switch it off, so we go from position A to position B, disconnect the battery and connect these 2 components in series, the current is going to try and fall immediately from steady state 1 amp to 0 very quickly. It's going to induce a voltage in the coil that's going to try and stop that current from going down. So the current does that, yeah, exponential fall towards 0, and if that does that, then the resistor voltage must, in the previous slide, follow it. Yeah. It's all down to Lenz's law and this induced EMF opposing the change that's causing it in the first place. Alright? That's quite important to understand that, so that you'll understand what we do when we talk about in AC circuits next week. Okay? So you've got all the formulas you need. This one is inductor and resistor voltage. At switch off. And the last one just one point about this induced EMF. If you have high value inductors at switch off, you can get some unwanted effects. What's going to happen is the energy that's stored is either going to be expressed as an arc across the switch terminals when you break them. So if you look at normal switches for lights, for instance, and what you'll find is they're rated so many amps resistive load, less current inductive load, and that's because the inductive load is going to cause arcing when you open the terminals, and that will make the arc, and that can be quite destructive. The other thing that can happen is this high induced EMF, if you're working it with where you've got electronic sensors on a machine connected to the coil of a relay, when you break it, that induced EMF can send a current back up the line and zap sensitive electronic equipment. So what they do is they put a diode in that will allow that current to dissipate in a circle around the coil instead of going back up the line. So there are implications to what happens. That's done electronically now, but the spark that ignite the fuel mixture in your car years ago would have been done with a very bit high inductance. Break that circuit, produce a very high 25,000 volts, 15,000 volts that cause that little spark to jump across the gap in your spark plug. It's not. I don't believe that's done that way anymore, but that used to be. It's probably electronic now. Alright? So it can be useful, but it can also be a problem. Breaking inductive circuits. Yeah. When you switch transformers on, they have an inrush current, because until that back EMF has built up, take a lot of current. You have to put special circuit breakers, transformer rated circuit breakers in, otherwise they'll trip when you switch on, and that kind of thing. Okay, so that's your inductor stuff. There's a couple of problems in your notes to have a go at on them, and there's some extra problems at the end as well. All right.